All right, any questions? On the chapter 18 homework or sample test?
Number 5 on the multiple choice for the practice test says, I wish to precipitate magnesium hydroxide from a 0.2 molar magnesium 2 plus solution. How much hydroxide is required to precipitate?
Okay. So whether we look at precipitation or solubility, we always draw the equation the same way. The precipitation would be backwards of this. In Chem 1A, your answer would be quite a bit different. You know, if I have 0.2 molar magnesium 2 plus, then in order to precipitate all of it, I need twice as much hydroxide because it's a 1 to 2 mole ratio. And so in Chem 1A, you would answer 0.4 molar would be required to precipitate out all the magnesium 2 plus. But in Chem 1B, this is a KSP problem. And the KSP is going to be the magnesium concentration at equilibrium times the hydroxide ion concentration squared at equilibrium. And so what we want to do is we want to precipitate all of this. That means initial we want 0.2, and at the end of this we want 0 molar at equilibrium. That's all 100%. So this would be 100% complete precipitation. 100% complete precipitation means that at equilibrium I need to put 0 in here for my concentration of magnesium times the hydroxide ion concentration squared at equilibrium. And so the hydroxide ion concentration at equilibrium has got to equal the KSP divided by 0. Well, anything divided by 0 is going to approach infinity. And so I would need infinity molar hydroxide in order to make my magnesium concentration 0. And so that would be the difference between a Chem 1A, which is a stoichiometry, versus a Chem 1B, where we have to use the KSP to determine it. Okay, other questions?
Number 9.
Number 9 on the sample?
Yeah.
Let's take a look. I'm going to pull up the sample test. There are going to be other questions.
Yeah, sure.
All right, so if we look at last year's test, number 9, a solution contains initial 0.2 and 0.4 molar hydroxide. So it's magnesium hydroxide again. So if we start off at 0.2 and 0.4 molar, we know we can't precipitate all of it, and because there's going to be a little bit of magnesium left over, unprecipitated, based on what KSP is. And so there are two ways of dealing with this problem. One is I could just do a minus x minus 2x. This would be called precipitation, because I'm going to lose some of that. You know, because the KSP for this is like 10 to the minus 11. The KSPs are going to be given. I'll probably write them on the board or see a handout, or maybe I'll try to put it in the test itself. So the KSP is like 10 to the minus 11. For sure, QSP is greater. We're going to have precipitation occur. But, you know, with a KSP of like 10 to the minus 11, we're going to get a lot of precipitation occurring. Right? And so this is like lead-2 iodide. You know, PbI2, yesterday, I told you, you could start off with a 1 to 2 ratio, let's say 0.1 molar, 0.2 molar of lead ions and iodide ions, and just let it precipitate in visual Mintech. Or the other option is just to start at pure solid. If you just start off at infinite solid, like PbI2, then that's like resetting it. And you know, I wouldn't bother doing this because since the precipitation is going to be a very high percentage, it might be like 0.199999999 molar precipitated, and your calculator is going to round that to 0.2, which is going to be 100% precipitation, but that can't happen. You can't have 100% precipitation unless the hydroxide's in infinity, right? And so what we do is reset this. If I reset this, then I'm going to shift all the ions. Well, it's a 1 to 2. There's no limiting reagent. It's stoichiometric. So I reset it to 0 and 0. And so there's two ways to figure out what the solubility is of magnesium hydroxide. One, you could start off with the ions in the right ratio, or two, you could just start off resetting it and just have solid. So just put the solid in water and let it dissolve. Well, because of round-off error, this is usually easier. You know, just reset it. You're going to get plus S plus 2S, S molar, 2S molar here. And then we calculate S. You know. S is going to be the equilibrium concentration of magnesium 2+ that remains unprecipitated. And so we can get the percent Mg2+ remaining unprecipitated or remaining in solution. And that's going to be, you know, however much I have here at equilibrium over my original. The original amount of magnesium is 0.2 molar. And so this should be 0.2 molar here times 100%. And then the percent magnesium precipitated is just going to be the difference here. It's going to be 100% minus the percent remaining. And so that's how you would solve this particular problem. It's going to be one of those, I think. Well, anyway, we have two definitions for complete. You know, complete 100% or just a complete precipitation. Complete precipitation means what? Is it possible to get a 100% precipitation?
No.
It's impossible. And so for us, complete is going to mean 99.9%. That's correct. So we'll see if 0.4 molar was enough for complete precipitation or not. Maybe we'd have to use higher hydroxide. But that's all we were given in this particular problem. All right, any other questions on the sample test?
For the KSP, it's like opposite. So if it's like bigger, that means that it's less soluble, and if it's smaller, it's more soluble.
If the KSP is bigger, then you get more ions. The KSP sometimes it's called the ion product. And so you get more ions, which means it's more soluble. The more ions you have, the more soluble. And so bigger KSPs means more soluble, smaller KSPs less soluble. But you have to qualify that because sometimes it's easy to compare the KSPs directly. Sometimes it's not. It depends on how it splits apart. And so an example, this came up earlier today. But let's look at the difference in KSP between silver chromate and silver bromide. If you look at silver bromide has 10 to the minus 13. It's not very soluble, pretty small KSP. If you look at silver chromate, its KSP is 10 to the minus 12. So this KSP is bigger. Since the KSP of silver chromate is bigger, then you'd say, oh, silver chromate is more soluble. But you can't say that. The reason you can't say that is because silver chromate ionizes in a different pattern than silver bromide. And so the KSP dependence on solubility is going to be different. And so if we look at it, okay, the KSP of silver bromide is smaller than the KSP of silver chromate. But what about the solubility? Well, the solubility is tricky because of the different splitting patterns. Is that how you spell tricky? Different, I'll just say deceptive. Better. Because of the different way they ionize. And so if we're looking at silver bromide, we start off with pure solid and let it dissolve. And so initial it's 0 and 0. And that equilibrium would be S and S. And so the KSP is equal to the silver ion concentration times the bromide ion concentration, which is going to be S squared. And so S, the solubility, is just the square root of the KSP. Well, you know, the KSP is like 10 to the minus 13. So half of that would be like 6.5. So it'd be 10 to the minus 6, 10 to the minus 7. 10 to the minus 6, 10 to the minus 7. Solubility. Whereas when we look at silver chromate, it splits differently. This is going to split up into 2 silvers and 1 chromate. And so initially we'll just assume that everything is just all solid. So we're going to have 2S and S here. And the KSP is going to equal the silver ion concentration squared times the chromate ion concentration. So this is 2S squared times S. This is going to be 4S cubed. And so the solubility is the KSP divided by 4 to the 1/3. So we're just going to do an order of magnitude here. It's 10 to the minus 12. So 10 to the minus 12 divided by 3 gives you about 10 to the minus 4. So the solubility is about 10 to the minus 4 here. And so even though the KSPs only differ by 1 order of magnitude, their solubilities differ by like 2 to 3 orders of magnitude difference in the solubilities. And so you have to watch out because the splitting can trick you, and sometimes what I'll do is I'll adjust the condition. I'll adjust the conditions. I'll just tell you this because it's tricky, and I'll try to trick you. I'll try to trick you in the sense that I give you one solid with a bigger KSP than the other, but I change the initial condition, or I change the splitting pattern, you know, I just choose whichever one, so that the one with the bigger KSP is actually less soluble than the one with the smaller KSP, okay? So watch out for that. I'm not saying I'm going to do it on this test, but you have to be careful.
So when it says a solution, if it behaves like the least ideally, that means it's the least soluble?
No. No. What causes things to deviate from ideal behavior for solutions? That goes back. There's two things that that cause a solution to deviate from ideal behavior, essentially. And the two things are pretty much related. It's just the strength of the interaction is different. These things will have an impact on the solubility, but you can't tell just from the solubility itself which one's more ideal and which one's less ideal. Although the interaction is going to depend on the concentration. So if we go back to chapter 14, or 13, go back to chapter 13. We're in chapter 14 now. We look at this table. This table is showing deviations from ideal behavior. And so what two factors in this table are responsible for non-ideal behavior? So the ideal is in the far right column, 2, 2, 3. But when you look at the columns are getting further and further away from ideal as the molality increases. So as the concentration gets higher, things behave less ideally. Well, solubility can have an impact on the concentration, but that's not something we have control over necessarily. So at higher concentrations, we expect greater deviations. Most of the salts that we're dealing with in chapter 18 have very low solubilities, like 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, right? And so they're going to behave somewhat ideally because of these lower concentrations. So what other factor causes things to deviate from ideal behavior? The charge. The higher the charge, the greater the deviation from ideal behavior. And both of these influence the formation of these things. What are these things called? These clusters, or what do you have a name for them? Call them ion pairs. Even though there could be more than a pair, they're just called ion pairs because you get a positive and negative pairing up or clustering up, okay? And so the higher the concentration, the greater the population of ions, so the more likely you're going to form ion pairs, right? The higher the concentration. And the higher the charge, the stronger the attraction, according to Coulomb's law. This is back in chapter 1. Okay, so ion pairs, an ion pair formation causes deviations from ideal behavior. And then later on in chapter 18, we see another factor here. Which is the salt effect. This is another deviation from ideal behavior. And the salt effect is similar. It's just an ion pairing, except not between ions of the solid, like for example, silver ions and chromate ions, or silver ions and bromide ions. These would be other ions that might be present. So if we had a salt like potassium nitrate, then we can get ion pairing between the ions in potassium nitrate, which have nothing to do with this equilibrium and itself. There's more ion pairs that can form. For example, when you did your calculation yesterday, did you see the hydroxo complex of lead? It's a hydroxoplumbate ion, or actually it wasn't plumbate, it was hydroxo lead. Lead 2, PbOH plus. Did you see that complex in your calculations? No? Visual Mintech, when you calculated the solubility of PBI in water, did you see this species on the list? If you didn't see this species, then something went wrong. This species should have been there. Where did the hydroxide come from? That came from water. And so this would be an ion pair with hydroxide as an external ion. So this would be ion pairing with external ions. Let's say potassium nitrate here. Let's say, so going back to this particular problem then, which one is expected to behave least ideally? Well, they don't tell us the concentration, so we'll assume the concentrations are the same. The concentrations are the same then. Copper sulfate is the correct answer. Why?
2 plus, 2 minus.
Yeah, 2 plus and 2 minus. Right. Magnesium has a 2 plus, but the chloride's only 1 minus. So if you got a pair between a magnesium 2 plus and 1 chloride, it's not as strong as a pair between copper 2 and sulfate 2 minus. All right, other questions on the sample test?
Number 11.
Which is more soluble in acid than in water? Acid is H3O plus, right? And so we figure out, as H3O plus is external ion, we got to figure out how H3O plus will impact the equilibrium. And we usually look in terms of Le Chatelier's principle. You know, how does it perturb the KSP equilibrium? And so if we go to the first one, does H3O plus interact with silver ions? No. Do they react with chloride ions? If they react with chloride, what do they form? HCl, is that a favorable reaction? It's going to form HCl in water. We know that this is not favorable. Chloride, how strong of a base is chloride? Number one, chloride is good at neutralizing acid. So let's say I had an upset stomach. Somebody was asking me about what was it? It's the one with bismuth in there. Pepto-Bismol. They're asking me about Pepto-Bismol. Something like that. Well, if you run out of Pepto-Bismol or something like that, why don't you just use some sodium chloride? Table salt, that'll help neutralize your stomach acid. Is that a good idea or? No, it's not a good idea because chloride is such a weak base that we consider it not even basic, we consider it neutral. In other words, HCl is a strong electrolyte. It hydrolyzes water 100%. This reverse reaction has a K that we call very large. And so HCl plus is not going to react with chloride. If I have an the only way we can get 3O plus to react with chloride is to eliminate the water. Or, you know, we heat it up and drive HCl off as a gas, you know. Because once you evaporate all that water away, then, actually before the water evaporates, the HCl evaporates. You know, it's like sodium chloride. The way we can get sodium ions and chloride ions to precipitate out of water, do you know how? The way we can get sodium ions and chloride ions to precipitate out of water is just to evaporate the water. Once you evaporate the water, then you'll get sodium. They're forced to come together, right? They have no choice because there's no more water left. Well, that's the same thing with this. You aren't going to get any reaction, so there's no reaction that occurs. So this doesn't impact that at all. So the solubility of this in acid and the solubility of this in water should be the same, except for the uncommon ion effect. What's the uncommon ion effect? The uncommon ion effect is, it depends on the acid that you add. And so the interaction here is going to be minor. The interaction here is that the hydroniums will pair around the chlorides. They don't react, they pair. Right? This. And then the silver ions will pair around, let's say I added nitrate. And so the silver ions will pair around nitrates. And so this will increase the solubility slightly. Right? But this kind of effect, what we call the salt effect or the uncommon ion effect, impacts all of these the same. Well, actually, this would be a stronger interaction, this is a weaker interaction because of the charge. But you know, it's a minor interaction. Whereas there could be a more major interaction. The more major interaction would be, if we look at the next one, calcium sulfate. This one is going to be much more significant because I know something about sulfate. Sulfate is a weak base. Sulfate being a weak base can be attacked by hydronium. Hydronium will attack sulfate to form HSO4 minus from water. A common mistake with this is people like to put two hydroniums. They like to put two hydroniums because they want to make a sulfuric acid, H2SO4, and two waters. But we don't do that. We just do one when we attack individual species. The only time you attack with two hydroniums is when you have a KSP double dagger. Do you guys remember the KSP double dagger? The only time we attack with two hydroniums is if we had something like copper sulfide. The KSP double dagger, the sulfide's too powerful a base. We're going to Cu2 plus HS minus plus OH minus. Here we have two bases. OH minus is the strongest, so we attack that one first. But HS minus is also a pretty decent base, and so that gets attacked second. So both of these get attacked.
So that's only when two bases are
You know, only when two bases are present. Otherwise, we just attack one hydronium at a time. In chapter 18. And we aren't going to do step 2 for this. We don't attack the next one because, you know, even though this is amphoteric, you know, its base strength is very small. And so this one, the hydronium is going to remove the sulfate. As the hydronium removes the sulfate, this shifts the equilibrium to the right, meaning this is going to be much more soluble in acid than in water. This one, you know, magnesium ions are neutral, chloride ions are neutral. So this one's like, you know, silver chloride. And so the answer to this is B, because the sulfate will be consumed by the acid. Uh-huh.
So generally, the stronger the base, the more solid.
In acid.
Um,
Okay, what else? Uh-huh.
number 12.
write the chemical reaction associated with K. When you see a KSP double dagger is for sulfides. And so we know sulfide is too strong of a base to exist in water. And so a lot of people, when they did number 12, this is last year's test, not a lot of people. A few people wrote this, you know. A few people wrote FeS solid goes to Fe2 plus sulfide. But it turns out that's not KSP, you know, or KSP double dagger. This double dagger is associated with the sulfide here. The problem with sulfide is it's a strong base. Strong bases hydrolyze water completely. Right? Strong bases hydrolyze water completely. You can't stop it. Once that sulfide sees water, it's going to hydrolyze it to form HS minus and OH minus. Since we can't separate these two, this is going to happen as one process, then the KSP double dagger is this. It's just going to be FeS solid plus water yields Fe2 plus HS minus plus OH minus. So that's the KSP double dagger equation. This is not KSP or KSP double dagger. And so when you look at a chart of KSPs, you know, they're just warning you. For example, in Appendix D, they use, rather than double dagger, they use the footnote B. And so they call it KSP B, you know, in Appendix D. And so this is called KSP B. In other charts, it's called KSP double dagger. So just you've been using KSP double dagger rather than B. Okay, other questions?
What about number 3?
Number 3. A lot of people say that test questions are nothing like the homework. So sometimes I like to put homework questions in the test. And so number 4 is a homework question.
Oh, number 3.
Number 3. Number 3 is, which solution will dissolve the most silver chloride? And so what you want is, you want to do this Le Chatelier type effect, you know, like we did here. If we can decrease the sulfate concentration by attacking it in some chemical reaction, we can increase the solubility. So we remove the sulfate, Le Chatelier's principle says it's going to shift right. And so if we're looking at the solubility of silver chloride, we want to attack either silver ions, or we want to attack chloride ions and remove those from the equilibrium to shift this to the right. And so we look at each of these and see which one. Well, you know, it's going to be soluble in water. Its solubility is quite low. But if we add silver nitrate, excess silver nitrate, that's a problem, because if we add more silver here, then the silver ion increases and shifts it left, which means that it becomes less soluble, right? So silver nitrate would be a bad choice because pure water will dissolve more than silver nitrate AQ. And then we go to ammonia. So how does ammonia attack? Does ammonia attack silver ions? Yes, ammonia attacks silver ions. We did this in the lab, actually. The ammonia and Lewis acid-base reaction, they're going to form the diamine silver complex. Here. How favorable is that? Well, it turns out it's really favorable because if we look at the KF, this is a KF. If we look at the KF value for this, it's pretty big. So let's take a look at Appendix B and see what the KF value is. Try to memorize the page. KSP2. KF must be after that. Here it is. So I can get a gauge of how favorable that is by looking. It's 10 to the positive 7. It's huge K, which means that ammonias are going to love to attack the silver ions, right? And so silver chloride should be much, much more soluble in ammonia than in water. But what else do we have? So let's take a look. So we got the ammonia for sure, but sodium cyanide. Cyanide is cyanide is a good Lewis base. Cyanide is really good Lewis base. How do I know? Take a look at this. Look at the first complex up here, the dicyanoargentate. Look at the K value, 10 to the positive 18. What's better at reacting with silver ions? Would it be cyanide or ammonia? Cyanide. Cyanide is like 11 orders of magnitude better at extracting silver. And so if it boils down to ammonia versus cyanide, cyanide for sure would be better. Removing silver ions and shifting the KSP to the right, making it more soluble. But let's see what our other choices are. Our other choice is thiocyanate, sodium thiocyanate. Thiocyanate is another ligand. And so let's look at the thiocyanate. This is tetrathiocyanate complex of silver, which we call tetrathiocyanate argentate 1 ion. Has a net -3 charge. And it's 10 to the positive 10. And so let's rank them. It's going to be most soluble in what? Cyanide. Then? Yeah, thiocyanate. Then? Ammonia. Then? Water. And silver nitrate would be the least soluble. Okay. All right, any other questions on the practice test? Or, I shouldn't call this practice test. This is last year's test. On last year's test? 16? 16, if 5 liters of blood to 4 sig figs is mixed with 12 milliliters of sodium cyanide, what percentage of free iron 2 remains? Cyanide, you have to watch out because it's an excellent Lewis base, right? Likes to attack metal ions. Hemoglobin has iron 2 ions stuck in the center of those things. And so cyanide likes iron 2 in blood. How much does it like iron 2 in blood? We could look at the KF. Take a look at the KF value. The KF for hexacyanoferrate 2 is 10 to the positive 37, which means that it's huge. Cyanide is going to pretty much eliminate any iron or react with any iron present, in solution. Well, that's not good for blood because you need the iron 2. You need O2 is a ligand. Is O2 a very good Lewis base? Not really, but that's good because it can get stuck on there and break off, You don't want something that's permanently attached. Cyanide's going to just permanently attach itself to the iron. So this problem is a solution dilution followed by KF, right? So doing number 16, this is just assuming there's 5.000 liters of blood. Yes. The blood is going to have a iron 2 concentration 1.3 times 10 to the minus 5 molar. Then we're going to add some milliliters, 12.0 milliliters of 0.039 molar sodium cyanide. And so what we're going to end up with is total of 5.012 liters at the end. We'll just make the units the same. And so the sodium cyanide concentration is going to equal, it's going to be 0.012 over 5.012 dilution of 0.039 molar. So what does that come out to? Well, yeah, whatever comes out. We can calculate that in there. Well, this is going to be the same as the cyanide ion concentration, right? Because for every 1 mole of sodium cyanide, we get 1 mole of cyanide itself. And then we can figure out the iron 2 concentration. The iron 2 is going to be a 5.000 over 5.012 dilution of 1.30 times 10 to the minus 5 molar. And so this is going to give us our initial iron and our initial cyanide. And then this is a KF, so we know iron 2 plus how many cyanides? How do I know how many cyanides attached to an iron? Oh, because it's given here. So iron 2 plus how many cyanides? 6 cyanides is going to give us the hexacyanoferrate 2. Hexacyanoferrate 2 ion has what net charge? Yeah. So we get that. And so we just plug in our initial concentrations here. What was the iron 2 again? The diluted concentration? What was it again?
Like a 1.29 times 10 to the negative 5.
Okay, 1.29 times 10 to the negative 5, thanks. And the cyanide concentration?
9.34 times 10 to the negative 5.
Okay. And then the complex concentration should be 0. Kf, this is a Kf equation, it's formation. It's different than the KSP. KSP is breaking things apart, Kf is putting them together. People get this mixed up all the time. Like in this example, people are writing KSP backwards and Kf is backwards. They didn't have it well memorized. Maybe they didn't have enough practice. And so the Kf equation is going to be the concentration of the complex. I'm not going to write the brackets for the complex because it's brackets on brackets. Well, I better because I wrote it in brackets here, so I'll do that. The concentration of the complex over the concentration of iron 2 over the concentration of cyanide raised to the 6th power. This is a 7th order equation. 7th order equation is not going to be easy to solve, right? Unless you know some tricks to solve this. Some people say, I don't need any tricks to solve this. I have a pretty good calculator, programmable equation solver calculator. Then I said, okay. This is years ago. Years ago we allowed programmable calculators. So people could solve these 7th order equations just by putting in a calculator. So I had to think of a way to get their calculator to fail, which wasn't hard. Their programmable calculator will fail in this problem. Why? Look at this. This is 10 to the 37. You know what their programmable calculator is going to say? That at the end of this, they get 0 molar iron 2 plus remaining, because their calculator will say it's x is 1.29 times 10 to the minus 5. Is that possible? Could we have 0? In order to get 0 iron 2, what is the molarity of cyanide that I need? Infinity. So it's impossible, right? The calculator failed because of round-off error. You know, the calculator wanted to say it's 1.28999999999 whatever, but it just rounded it to 1.29. And so, so even though they argued that they didn't have to do any trick because modern technology, you know, living in the Stone Age. Okay, that's one. And then 2 is, even with powerful computers, you have to make assumptions to solve some problems. And so, well, you know, a trick like this, when you see a huge K like that, what do you do in order to solve this problem? Because if you're using successive approximations, you're going to have a huge headache for this. You reset this. If you reset this, then the simplifying assumption works, and it means it's a very easy problem to solve mathematically. So the people who don't reset this try successive approximations and end up not completing the problem because they're guessing x is equal to 1.289. No. X is equal to 1.2899. No. X is equal to 1.28999. You know, they're going on and on. It's hard to get it to converge. So we reset this and then solve it. What was the problem with this? Is setting it up or solving for x? Vaughn. So if it's set up like this, then you can figure out the rest. Well, anyway, we could set it up. If I reset this, tell me what it resets to. What does iron go to? Well, which one's the limiting reactant? The cyanide? We need 6 times as much cyanide as iron. So we're going to figure it out. Assuming the solution dilutions are correct, it looks like, well, what's 6 times 1.29? What is it? 7.5. So we have more than 7.5. We have 9.34. So our ions are limiting reagents. So we'll go this. And so we need 7.5. Just 7.50?
I got 7.74.
7.75? 74? 7.74 times 10 to the minus 5. Right? Would be this would be minus y minus 6y. So if y is 1.29 times 10 to the minus 5, then 6y is 7.74, right? Times 10 to the minus 5, which is going to give us a 0, 13 would be 6, 8, 1. 1.60 times 10 to the minus 5 molar. And then this would be plus y. Plus y is going to be 1.29 times 10 to the minus 5 molar here. So the change here is going to go this way. So this is going to be plus x plus 6x minus x. And so at equilibrium, I'm going to get x molar iron 2, 1.60 times 10 to the minus 5 times 10 to the minus 5 plus 6x molar, and then 1.29 times 10 to the minus 5 minus x molar. I'm plugging this back in here, so this is 1.29 times 10 to the minus 5 minus x. This is going to be x. This is going to be 1.60 times 10 to the minus 5 plus 6x raised to the 6th power. Looks like a horrendous math problem to solve, but we have another trick we can do. What's the other trick we can do? We use the simplifying assumption, and then it's easy. So the simplifying assumption should work well because x should be very small going backwards. X is huge going forward. So this is going to give us 1.29 times 10 to the minus 5 divided by x, 1.60 times 10 to the minus 5 raised to the 6th power. Solve for x. Okay. It becomes a pretty easy problem if you use reset and your simplifying assumption. It becomes a very difficult problem if you don't reset. All right, was that it for the questions, or are there any other questions on this? Are you good? How about the chapter 18 homework? Questions on that? Yes.
For iron, you put 1.29 and on the paper is 1.20. Did you do that because like you can't have complete 100% reaction?
No.
That was just an accident.
No.
Oh, solution.
Solution dilution. It was because you're mixing two things together. You got to do solution dilution. So it went from 1.3 to 1.29 because we added some more liquid. That's fine. Okay, anything else? This? No? All right, we're going to continue with kinetics. Tomorrow, I had the strength of acids lab, but what we'll probably do tomorrow is, since it's an exam day, we'll probably postpone that. And so tomorrow in the computer lab, we're going to do the titration and kinetics. Just continue that. Going back to kinetics, we have A goes to product. This is just a single reactant. Then there are going to be three possibilities for this kinetics. I mean, there could be more. There are only three possibilities that we're going to look at for the kinetics. And that is, it could be zero. If it's zero order, we can see it from the shape of the curve. If it is zero order, then a plot of concentration of A versus time is linear, right? Or it could be first. If it's first order, then the concentration of A versus time is nonlinear, but we can recognize it based on the shape of the curve, which is going to be slightly different than second order. Second order doesn't decay like that. It decays a little differently. And so looking for patterns in these curves, we talked about the half-life. For example, if I cut the concentration of A in half, how long does it take? That's what we call the half-life. And then I cut it again in half. And then again in half. What's happening to each of these half-lives? You see, they're getting shorter and shorter. In fact, the second half-life is 1/2 the first half-life. So it's always 1/2 the previous half-life. So then we can see. Whereas if it's first order, then what happens with the half-life in first order is they're the same. Like the first half-life is equal to the second half-life. In fact, all the half-lives are the same. Whereas if it's second order, then I look at the successive half-lives and it's doubled. And so the first half-life, let's say, takes this long. The next half-life is going to take twice as long. And so the three choices we have are, one, the half-life is decreasing, the half-life is constant, or the half-life is increasing. So the half-life could double. And so this gives us a way to determine, just by looking at a data table, how to determine what order it is. And so we started off with determining the order. And we can do this qualitative. For one, we look at the data table. And so if we have a bunch of data, then hopefully we have something like this, where see the data table here. Look at the time. Usually you put the time first and then the concentration. And so we look at the data table, time versus the concentration of A, and we say, well, initially, let's say we have 1.0 molar or something like that. Then we look, how long did it take to get to half the concentration? And then if we cut it in half again, how long did that take? And so we have three possibilities. It could take less time, it could be the same time, or it could take more time. And so let's take a look at this data table here and see, can we determine the order just by looking at the data table? And so we started off at 1 molar here, and so we want to go to about half. Well, 0.47 is close enough to half, right? So we cut it in half, it took 75 seconds. And then we go from about 0.5, we want to go to about 0.25. Well, 0.22 is going to be as close as we're going to get. And that's going to take, well, that takes us to 150, so it takes us an additional 75 seconds. And then from 0.22 to about 0.1, well, there's not much data here, but we can already tell that this is going to be first order. And so this data is showing first order. And so, well, this is another experiment, another reaction. So let's see about this one. So these two data tables aren't related. And so we're just looking at another reaction here, completely different reactant. And then let's take a look. Tell me what order this is. First order again? Zero order? Zero order? Well, let's look. It took how long? It took 50 seconds, and then the next one took only 25 seconds to cut it in half again. And so the second half-life, which is going from 50 to 25, took us from 50 seconds to 75. So this has got to be zero order. The half-lives are getting shorter. Right? For zero order, we can have complete reaction. Zero order, boom, at this time it's done. But for first order and second order, how long would it take to have 100% reaction? A long time, infinity. For first order and second order, we usually say, okay, 99% is long enough, that's enough, that's complete. Say, cut it off there. But here, this is kind of weird because we'd never wait until this gets to zero. How long would you have to wait for this to get to zero? Too long. And so you'd say, well, after 99% reaction, maybe we'll call it complete or done. Well, let's take a look at this data table here. So from 100 to 0.5 took 100 seconds. Then 0.5 to about 0.25 is going to take more than 100 seconds, less than 100 seconds, or about 100 seconds? It's going to take more than 100 seconds for the next half-life, which means that this has got to be second order. So this is easy. This is first order, this is zero order, that's second order, just by looking at the data table, right? You can also do that looking at the graphs. If you look at the graphs, you try to visualize what's going on. You can look at the graphs and just look at the half-lives, right? And then see. The problem is sometimes the graphs don't show. Like sometimes you'd like to get 99% reaction, but sometimes people stop and they only get like 10% reaction. If you only got 10% reaction, then can you tell? So, no, it would be kind of hard to tell because we can't do this. So, for example, tell me what this is. here they wrote the molarity and the time opposite. And so, tell me, is this first order, second order, or zero order? We can't really tell because we want to go from 1.5 to 0.75, but there's no 0.75 here. There's not enough data, right? So we cannot tell there. So if we don't, like, so for example, if part of the graph is missing, a large part of it, so we only have this much data. We don't have this much data. We only have this much data. So they kind of look all the same, you know? How can you tell the difference between these three with minimal data? Like this. Is it easy to see? Can you eyeball it? No. And so this is what we're going to do. Yeah, kind of like that. If it's hard to eyeball it, you know, data table or graph. And so just estimate. T1 half. If that's hard to do, then what we can do is we can do graphical analysis. So whether we look at this data table here or graph this, it kind of looks the same. For I can't tell if it's zero order, first order, or second order. And so as far as graphical analysis goes, this is what we're going to do is we're going to make plots. And so we're going to extend the data table. In fact, what we're going to do is we're going to take the time, we're going to take the concentration of A, then we're going to take the ln of A, and then we're going to take 1 over A. And okay, so this is the experimental data here. And then we're going to calculate this over here. Just by either using calculator, punch it out, or using Excel to do the formulas. Copy them, paste them down. Okay. And then we're going to make 3 plots. So we construct 3 plots. These are based on integrated rate laws. Did I talk about integrated rate law? Yes or no? Talk something about it? Oh, okay. Yeah. The initial. Well, let's talk about this plot. Did I talk about the changing slope? You know, if the slope is always changing. So if we have 0 order, then there's a way to describe this, right? 0 order is linear when you plot out A versus T. And one way of describing it is the rate law. The rate law shows how the rate, that is the slope, and the rates are always positive. The slope here is negative, so we multiply this by negative, or we use absolute value sign. We multiply by negative to make it a positive because rates are always positive. And the rate law this is the rate constant times the concentration. If it's 0 order, then the power, the concentration is raised to is 0. And so anything raised to the 0th power is 1. And so this is just equal to k. In other words, the slope is constant. It does not depend on the concentration. All right, so this just tells us how the concentration impacts the slope. But let's say I wanted to know how long it takes. In this case, I could figure that out. There are two ways. I could use algebra or I could use calculus. If I use algebra, then I can figure this out. Delta A, change in concentration, is equal to, I'm going to rearrange this, minus K times delta T. Delta A is A final minus A initial. A initial I'm going to call A times 0. Minus K. Delta T is T final minus T initial. What is T initial usually in a kinetics experiment? 0. If T initial is 0, normally it's 0, then this is just equal to minus KT, which is just what time you got. And so we end up with A at time t is equal to minus KT plus A at time 0. In other words, this is equal to y equals mx plus b. This is called the integrated rate law. This is very important because this allows us to determine how much at any time or how long for any concentration. So if we wanted a question like how long will it take to get 99% reaction, we could easily answer it using the integrated rate law. Calculus, the reason it's called integrated rate law is we do something in calculus called integration. And so if you take the rate law and integrate it, then we end up with the integrated rate law. And the integrated rate law here is A times t is equal to minus KT plus A times 0. Did I talk about the integrated rate law like this yet or not yet? Yeah. Okay, if it's first order, if we got a first order reaction, then the rate law looks a little different. The rate is going to depend on the concentration of A. And so the rate is delta A over delta T. We got negative, and this is equal to K A to the first. It's first order. And so the rate changes with concentration here. And we see that here. The rate changes with concentration. It's directly proportional. And so that is, as the concentration gets cut in half, the rate gets cut in half. So we get concentration versus time like this. But if I want to figure out how much or how long, can I use algebra? And so if I try to use algebra to answer this, let's try it up here. Let's try to use algebra. Then we get delta A over delta T. If I want to figure out how much, then I do delta A, how much, right? If I want how long, and then I figure out delta T, how long? How much? How long?
What is the reactivity, the concentration initial, EYPTE?
This one?
Integration after calculus integration.
To the left.
Oh, this one?
Yeah.
That was something I forgot to erase earlier. Sorry. That was experiment. Something I forgot. I just forgot to erase it. Yeah. Anyway, If I try to use algebra, then I can solve for it, right? Because this is equal to Ka to the first. And so what I'll get is minus, well, delta A is A final minus A initial, or A times 0. Delta T is T final minus T initial, which is equal to Ka. A is A at time T, or A final. Can I solve this for time or a concentration? Is this an equation you can solve for T or A? No. Algebra doesn't work here because delta A, delta T, the slope is continually changing. It's not constant. Whereas over here in zero order, it's constant, so we can do it. And so this is why we must use calculus. If you want to figure out how much or how long, you must use calculus. Must use calculus. Well, we aren't going to use it. We're just going to use the equation that comes from calculus. And the equation that comes from calculus for first order is the integrated rate law. And so what we do is we take the rate law and integrate it to get the integrated rate law. The integrated rate law looks like this. It's a natural log of A at time t over A at time 0 is equal to minus kt, where t is actually delta t. This is the time interval. Delta t. So there, now we can solve for how much or how long, either the time or the concentration. But this gives us another way. We could rearrange the integrated rate law. If we rearrange the integrated rate law, then an alternate form of this is ln of A at time t is equal to minus kt plus ln of A at time 0. In other words, this is y equals mx plus b. And so if we plot the natural log of A versus time, then this plot comes out linear. Oops, for first order. This is linear. And so another way of determining the order is to make a versus time, an ln of A versus time, and one more. And the one more is for second order. So we'll do the second order here. For second order, the rate law looks like this. The rate is equal to delta A over delta t, which is going to be negative, which is equal to Ka squared. So it's going to have a second order square dependence on the concentration, that is the slope. And we use calculus. When we use calculus, then we come up with this equation, the integrated rate law, which is 1 over A times t is equal to plus kt. It's positive rather than negative. And this is 1 over A times t, 0, sorry. 0 here. And so if it's second order, we make a plot of this, because this is going to be the equation of a line, y equals mx plus b. And so if we make a plot of 1 over A versus time, it's linear. It comes out a straight line like this. Whereas, if it's second order, second order, would have a nonlinear A versus time and a nonlinear ln of A versus time. ln of A versus time for second order is nonlinear as well. And so, the only one that's going to be linear is the 1 over A. And so this, if we don't have enough data that we can eyeball it, we can go ahead and plot it out and see which one is most straight. The A versus time, the ln of A versus time, or the 1 over A versus time plot. A being the concentration A. Okay. Actually, well, I have more time. I thought I was done, huh? 3 more minutes. And so, this is what we're going to do for this data. And the slope is going to be k for second order and negative k for 0 and first order. And so what we do is, and we could have done this for this data as well. Here, show you that data. Here, we can't eyeball it really easily, right? It's pretty hard to eyeball. But when you look at this, you know, we can make 3 plots. We have the A, concentration of A versus time. Then we have to use Excel to get the ln of A values. And we can use Excel to get the 1 over A values here. Make 3 plots and see which one of those is most linear. Usually the way we determine which one's most linear is we look at the R squared. Are you familiar with the R squared? R squared is the correlation factor, and the closer it is to what, the more linear it is. 1. An R squared of 1 is it's perfectly linear, the data. And so we look at which R squared value of those 3 plots is closest to 1. And we want a lot of 9s in that. Okay. And so that's a way we can determine it. But on tests, are you going to have Excel to graph or to calculate the R squared values? No. And so for tests, we have to come up with an alternate method. And this alternate method, I'll talk about next time to determine it. Okay. All right, we're done for 3 days.